Well, welcome everybody. Thank you very much for joining us today here. My name is Ian Mosley, and I'm joined here today by Jose from the University of Warwick. Jose will be managing our Q&A session at the end, and actually next week presenting some content on wide bandgap semiconductors. Today's session is going to be all about isolated DC to DC power conversion. Hopefully, we ran this session this morning, and we had some comments that people couldn't see my mouse pointer. Hopefully you can see it now with the red dot. If you have any problems with understanding what I'm saying, or you can't see the mouse pointer, please flag that up in the chat box. This presentation will be about 1 hour long, including about 10-15 minutes worth of questions at the end. If you look on the right-hand side of the webinar portal, you can see there's a place to put your questions in. There's also a chat box. Try to put your questions into the question bit rather than the chat box, and then we can look at those at the end. Jose will also be launching some polls as we go through the webinar, just to get a feeling about the sort of stuff you're interested in terms of power electronics. So please do engage with that if you're able to. So this is the third of our webinars in power electronics. Last week we were talking about AC to DC conversion and DC to AC conversion. Today we're talking about DC to DC conversion, and specifically isolated DC to DC conversion. And it's one of my favorite areas, actually. It's something we get involved with quite a lot. So I'm just going to share my screen. Hopefully you will all be able to see this okay, and I'll do my best to keep my mouse pointer visible. So here we go. In terms of what we're going to talk about today, I want to start from a sort of a general point. What do we mean by isolated DC to DC conversion, and what's the fundamental building block that all of the topologies that we can think about using to perform this function, what do they all share in common? I appreciate this 1 hour we've got is quite a short amount of time to talk in any real depth, and there are a multitude of topologies that you can actually use for isolated DC to DC conversion. So I've actually picked two of my favorites. If you can have a favorite in the world of power conversion, I've picked my two favorite. The first one is a flyback converter, and this is a very commonly used topology for fairly low power levels. The reason I've picked it is because you'll find this everywhere in all sorts of applications, in particular mobile phone chargers, that sort of stuff. And I find it's quite a useful way to explain one type of converter and how the energy is managed in that system. I'm going to then contrast that by talking in depth about another topology called an LLC converter, which operates in a fundamentally different way to the flyback converter, but they both use that same central element, which I'm going to describe to you in a minute. And then we've got the questions and answers at the end. So general isolated DC to DC conversion. At the heart of all of these topologies, the isolation barrier is formed by a magnetic component, a transformer, pretty much similar in theory anyway to the sort of thing that you would find converting 50 Hertz mains. The main difference is that these isolated converters, when you're running switch mode converters, are running at way higher frequency. So rather than running at 50 Hertz, they might be running at 100 kilohertz or even higher frequencies than that. The reason that that's important is as you go up in frequency, the amount of energy storage that you have to support within that component falls, almost as a linear function of the switching frequency to a certain point anyway. So if you want to make a high power density converter, you need to start pushing the switching frequency higher and higher. Now, that's the fundamental building block, but we're going from DC to DC, and transformers don't like DC. So on the front end of pretty much any converter, a DC to DC converter, you're going to find some circuitry which is going to turn that DC into a high frequency AC waveform, which is applied to the transformer primary winding. And the different topologies do that in different ways, but as a fundamental building block, that's what's going on. So we chop the DC input up into a high frequency AC signal, send it through our transformer at high frequency, and on the secondary side, we then rectify that, or just recapture the DC component to turn it back into DC. So we have this process of chopping the DC up into high frequencies, sending it through the transformer, and then turning it back to DC again. And this presentation today is just talking about the power topology. So we will come on to control and magnetics design in later webinars. So that's the basic description of how these things work. And in this example here, power flow is from left to right. It's a unidirectional power converter. However, as you'll see in one of the examples I'm going to give at the end of this webinar, it's possible to have that rectification and inverter circuitry actually being the same build, or one circuit performing the same function. So you can actually turn some converters into natively bidirectional capable systems by how you design them. And that's quite an interesting thing to do, because when you're looking at e-mobility, electrification of transport, if you're considering electric vehicle charging, well, if you want to support vehicle to grid operation, you need to be able to not only charge the battery, but also have the battery send energy back to the grid should you want to do that. And one of the topologies I'll show you at the end is actually a really neat way to do that at very high performance levels. So that's our general converter. If we then look at what the equivalent model is, or an equivalent model of our transformer, this ideal component here, in practice, you can see it's got a number of elements to it. So we've got an ideal transformer. We've got a magnetizing inductance here. That could appear on either side. You could put it on primary or secondary. Most people put it on the primary side just through convention. And that's just the fact that we've got a number of turns of wire wound onto a magnetic core, which gives us inductance. And that's the magnetizing inductance of that particular device. We've also, in parallel with that, got some resistance, and that's to model the core loss. So we're moving the core material through its BH curve. That incurs loss every time you do that, so we can model that with this resistor. We also have this leakage term here. If you imagine the windings, the primary and secondary windings on our transformer, well, they generate flux. And if any of the flux you generate in the primary winding doesn't link through to the secondary winding, essentially it's uncoupled and it forms a leakage inductance. So that's modeled by this effect, this component here. It's uncoupled inductance from the primary to the secondary. We also have some winding resistance here, and both the winding resistance and the effective core loss resistance are typically very non-linear with frequency, so that it can be quite difficult to model that. But that's our basic equivalent circuit that I'd like to use to underpin the rest of what we're talking about today. In terms of the equations, I've already defined these terms here. The ideal transformer here, the NP and NS, that's just an idealized transformer whereby the secondary is just a turns ratio multiplied by the primary voltage. And similarly, the secondary current is the inverse of the turns ratio times the primary current. So that's our ideal part. And then the other LM, LL, and resistors model the actual real physical attributes of that particular device. So that's our black box building component for our isolated converter. Now then, I was going to talk about a flyback converter, and I'm going to show you how we use this particular model to transfer power in a flyback converter. Now, if you've dealt with flyback converters before, this will become quite familiar, but bear with me on this. The way a flyback converter works, this is actually the topology on the top left-hand side of the screen. You can see we've got our transformer element here, which again is our, if you zoom in, is our equivalent circuit. There's a dot polarity, which is to do with the polarity of the winding voltages that we generate here. The way a flyback converter works is, you can sort of see it from the waveforms here, but I'll explain it generically. When MOSFET M1 switch is on, the dot polarity of our windings here means that the output diode is blocking. So during the on time of that primary side MOSFET, the secondary circuit is completely out of circuit. And all that happens is you just start ramping up current in your magnetizing inductance and leakage inductance as well. And what you're really doing there is you're storing energy in the magnetizing inductance of the transformer. Now, if you attended our webinars last week talking about switch mode power conversion approaches, I had this analogy of the magnetic element being like a bucket of energy. And that's the same thing that's happening here. The bucket of energy in this case is our magnetizing inductance, and we're just filling that up during the on time of the switch. When that switch turns off, the polarity of those two windings inverts, and actually we start to forward bias the output diode here. And what happens is the energy that we had stored in the magnetizing inductance during the on time of that MOSFET now freewheels through to the secondary side and is delivered to the output. So essentially, the transformer core is acting like that bucket of energy. If you actually measure the operating waveforms of that particular converter, you can start to see how that works. So if this hopefully has come out okay on your screens, the top plot here is the drain to source voltage across the MOSFET. And the bottom plot, the red colored trace, is the current flowing down through the drain. So when we turn the MOSFET on, in this particular case here, there's 0 voltage across the MOSFET because it's on. We impose about 340 volts because this is a mains power converter. We impose 340 volts across the magnetizing inductance, and you start to get a linear ramp up in current. Now, during that time, the output load current supported by the DC-DC converter is actually just sourced out of this output capacitor. So the output capacitor is also a bucket of energy supporting the output. When we reach a certain point of current, we turn this particular device off. And at that point, the current in the drains falls to 0 very, very quickly. During this flat region here that you can see on the voltage waveform, what's happening during that flat region is that the energy we stored in the magnetic core is now being released through to the secondary side. There's a spike here, and that's to do with leakage inductance. And I'll talk about that one in just a moment. When we get to the point where all of the energy we put into that core has been exhausted, well, the core voltage, the voltage across the primary then relaxes just down to the DC link voltage, and we get this oscillatory behavior. And then we turn the MOSFET back on. One of the key design parameters that we will use for a flyback is this VOR figure, which is actually just the output voltage multiplied through the turns ratio of the transformer. And that's actually quite an important design metric, and I'll talk about that one in a moment. So this is fundamentally how the flyback converter works. Now, this spike I mentioned here, the leakage spike, because in our transformer we have uncoupled inductance, well, during the on time of the primary side switch, we've got current flowing in that leakage inductance, which represents energy. And when we turn that primary side switch off, that energy in the leakage inductance can't make its way through to the secondary. It's uncoupled, and it has to go somewhere else. So what we actually do is we have a primary side snubber here, whereby we provide an alternative path for that energy to be dissipated, and that causes this voltage spike. If we didn't have that snubber circuit on here, this would cause an overvoltage and destroy the primary side MOSFET. It also gives you a feeling on why the flyback converter is only good at fairly low power levels, because it's quite hard to get the leakage to be very, very low. If you look at most flyback transformer designs, the leakage inductance, you're doing well if you get that to be about 1%, 1 to 2% of the magnetizing inductance. So you have to, well, unless you use an active scheme, you have to burn that power. So it causes an efficiency problem. This is really just describing what I've mentioned to you. I've mentioned these terms CCM or DCM, and I'll describe those actually in a little bit more detail on the next slide, if I may. It's to do with how we operate this waveform. So again, the energy in the leakage inductance is just dissipated in most cases because it's the cheapest way to do it. We need low leakage for high efficiency. One of the limitations of a flyback converter is the fact that the output capacitor here, capacitor C1, needs to support the output load current during the on time of the primary MOSFET. And then during the off time of the MOSFET, we have to have current flow into that capacitor to restore the charge that it has lost during the off time of that, during the on time of the switch. So what happens is, for a given level of output current, you end up with quite a high RMS current stress in this particular capacitor. And for that reason, you tend to find that the flyback converter isn't used for output currents more than maybe 3 or 4 amps. There's the odd occasion it might be, but most of the time this is used up for current levels of maybe 1 or 2 amps on the output. So unless you're delivering a very, very high output voltage, this limits the ability of the flyback converter to deliver particularly high current power levels. Most often it's used for less than 300 watts, and I would say the vast majority, the biggest volume is probably less than 50 watts. A brief definition of what I meant by this CCM and DCM operation. So DCM stands for discontinuous conduction mode, and CCM stands for continuous conduction mode. And it's really to do with how the energy in the transformer storage element, the magnetizing inductance, is being utilized. Those first scope plots I showed you on the previous slide were a discontinuous mode operation. And that's what you can see here. With discontinuous mode operation, when the primary side MOSFET turns on, it starts its current flow from pretty much zero, and you have a linear rising current until the switch turns off. If you then, at the same time, were to plot out the flux density in the transformer core, due to the magnetizing inductance, you would see a linear ramp in flux density coincident with linear rising primary current. And then when the energy freewheels through to the secondary side, we see a linear ramp down in flux density. But the important thing with DCM is that the flux density in the core reaches zero before we then turn on for the next switching cycle. So really what we're doing there is we're loading a finite amount of energy into the core, and all of that energy then is sent through to the secondary side, and we run with zero energy in the core until the next switching cycle. So that works just fine. Continuous conduction mode is slightly different. With continuous conduction mode, you tend to have a slightly higher primary inductance, and the result of that for a given switching frequency may be that during the on time of the switch, we actually start, when the switch turns on, we don't start from zero, we start from pretty much a non-zero finite level, and we have our linear ramp up in current. And then it obviously goes to zero when we go through the freewheel period. If you were to plot out the flux density at the same time, you can see here that the flux density now does not go down to zero at any point during that switching cycle. And that has some benefits, certainly for if you're going to higher power levels in flyback converters. The RMS value of the trapezoidal waveform for a given power level is always going to be less than the RMS waveform for a sawtooth. So you have a benefit in terms of reduced RMS current stress in the rest of the converter. The downside is you need more energy storage to do that, so you tend to need a bigger transformer core to support that. So hopefully that definition is reasonably clear. On this series, I've tried to avoid using too much maths to describe converters, and really I am going to share some equations now, but these are really just to support the concepts I've just been describing to you. So in discontinuous conduction mode, what actually happens is we're essentially charging energy into an inductor every switching cycle, and then releasing all of that energy every switching cycle as well. So the energy into an inductor is just a half L I peak squared. And that if we assume it's 100% efficient, which is a bit of a bold assumption, but for the moment, let's assume it is. If we assume all the energy is released during the off time of the primary FET, you can equate the output voltage through this equation here. And you can see that the output voltage now becomes a function of the magnetizing inductance, the switching frequency, the output current, and various other parameters here. The peak primary current, again, you can calculate using the same mathematical approaches. But the key thing, and the metric that we tend to take forward to the later development stages, if you're in DCM operation, a key metric is how much energy do you need to store in that magnetic core. And in the case of DCM operation, well, we just need to store enough energy per cycle such that the product of that energy multiplied by the switching frequency gives us our output power. So the core energy storage is just the output power divided by the switching frequency. It's different in CCM though. For CCM operation, this is a scope plot showing a different, actually it's a different flyback, but it's a flyback converter showing a CCM waveform. Because of the way the converter works, we find that the output voltage of that converter now is no longer a direct function of the magnetizing inductance and switching frequency. It actually reduces, at least to a first order, to be an equation that looks like this. Delta here is the duty cycle of the switch. You can therefore work out the peak primary current that you need to then support. And remember, the peak primary current you need to support is a representation of the energy storage you need to support in your transformer core. Now, it gets quite complicated to actually then give you an analytical expression for that. But the key thing about continuous conduction mode is that the core energy storage you need for a given operating point, if you want to run in continuous conduction mode, is always going to be more than it is for discontinuous mode, for the reasons I described on the previous slide. So the trade-off there is continuous conduction mode is fantastic to reduce your RMS current and the stress in the rest of the circuit. However, the price you pay for that is you may have to increase the core size of your magnetic or your transformer to support that. And the reason I keep talking about energy storage and core energy storage is that's a key metric that we take forward when we're actually designing the custom magnetics. And in one of our later webinars, we're going to go into a lot more detail on magnetics design. But a key input for that magnetics design is the energy storage that the core needs, or the magnetic component needs to support. There's a transition between the two. So we actually ran this webinar this morning, and we got a question from one of the participants. Will it not always transition from DCM to CCM at a certain load point? And the answer is yes. There's always going to be a load current for any given design, at which point the design will enter CCM operation. The key thing is whether you actually want that to happen or not. And then some applications, for example, quasi-resonant behavior systems, whereby you have that relaxation of the voltage ring, you actually want to make sure that you always operate in DCM operation. So you have to design your circuit appropriately. But this you can use all the maths here to work out for a given operating point whether you're in DCM or CCM. So hopefully that makes sense. There's quite a lot of equations going on here, and one of the best ways I've found to get a feeling of how these converters really work is to try and put all of those into a spreadsheet, because by doing that, it forces you to understand and work out the fundamental equations and put them all down, and then you can start to quickly vary parameters and see what impact that has on peak voltage stresses or peak current stresses, or whatever it is. It's quite a nice way to do it. I want to give you an example of a flyback converter. Was actually built by a summer student we had here at the company a few years ago, and we did this to give him a chance just to build up a flyback converter and understand how it works. So this particular flyback converter was a 15-watt output capable system. It was actually a split output, plus and minus 15 volts with half an amp on each. But from a point of view of designing the primary magnetic energy storage element, consider it to be a 15-watt converter. And the task we gave him is it had to operate from a 20 to 28 volt input and deliver 15 volts on the output. So it's not particularly high power. It's a fairly basic circuit. One key thing to do is, I talked about this VOR figure on one of the earlier slides, this reflected output voltage. Now, if you can target a reflected output voltage which is equal to your nominal DC input voltage, that means that if you do operate in CCM operation, your duty cycle of your switch will be almost exactly 50%. And the reason that that's quite nice is the way this converter works is, remember, during the on time of the switch, the primary side circuit is active, sending energy into the core. Then during the off time of the switch, the secondary side circuit is taking that energy and transferring it through to the output. Now, if we operate at an extreme of duty cycle, say 10%, it means that the RMS currents in the system on either one side or the other are going to be very distorted. So it might you'd end up pushing a lot of loss onto the primary or onto the secondary side. So if you can sit at a target of about 50% duty cycle, you nicely balance the stress on the two sides of that circuit. The primary clamp voltage, so remember the leakage inductance clamp that I showed you in the plot, you want to try and target that clamp voltage maybe to be about 1.5 times your VOR figure. If you use a much higher clamp ratio than that, you can imagine the voltage builds quite quickly across the MOSFET, so you risk damaging the MOSFET, or you have to overrate the MOSFET in terms of voltage. If you reduce that ratio too much and bring the clamp down to be close to the VOR, you get this weird sort of 1 upon X type relationship, whereby a bigger and bigger proportion of the energy that you were hoping would freewheel through to the secondary side, a bigger part of that actually leaks out into the primary side clamp. So you get a hit on efficiency. It's a bit of a balancing act, but a starting point of about 1.5 times VOR is a good point to target for your clamp voltage. Switching frequency, it's actually quite difficult sometimes to choose a switching frequency. It's a great place to start is around about 100 kilohertz. Most commercial flyback converters would probably be around that range, unless they're performing a particular function which requires them to operate somewhere else. You don't want to go too much higher than that, because if you're trying to meet EMI requirements, well, the fundamental for the EMI standards is typically 150 kilohertz it starts at, so you want to keep below that. You don't want to go too low in frequency, because the energy storage, therefore the size of your magnetic component, starts to get bigger. So that's the balancing act there. But 100 kilohertz is a great place to start. Depending on what you're trying to achieve, I quite like to use continuous conduction mode and target that for operation on the low line and maximum load. That's when you're going to operate in CCM. But it's okay to transition to DCM under different operating conditions. But I tend to target CCM operation just to keep those RMS currents down. Your cheat sheet that you build here, a key output of that is going to be the peak core energy storage, because that feeds in then to how you go about designing your magnetics. And you can see here I've highlighted, it's not a lot of energy we're talking about. So this is a 15 watt converter. We're storing 0.24 millijoules. So it's tiny amounts of energy, but you need to know how much that is, because that feeds into the later magnetics design. If you can automate capture of those resulting power component stresses, so I've done that here. You can see for the primary MOSFET, I've captured peak primary current, RMS current, peak drain source voltage, and power dissipation based on the RDS(on). You can start getting a very quick feel around the stress of your whole power stage for a given set of operating conditions. And it's all based just on the fundamental operation of that particular converter. This converter, I thought it'd be quite nice to put it on the bench in the lab and just show you some real operating waveforms here. So on this plot here, it's a video which I'm going to play shortly. The yellow trace here is the drain to source voltage across the MOSFET, which I've already described to you. It's that waveform that you can see here. The green trace is the gate, is the gate source. So that's the command signal for the MOSFET to turn on, going up to about 9 volts. When the MOSFET turns on, you can see the MOSFET voltage drops to 0. When the MOSFET turns off, you get the reflected voltage coming back. And on the bottom here, the orangey kind of colored trace, that's actually our output DC load current. And what I want to show you is the behavior of primarily the yellow trace, the drain source voltage, as we start to bring up the output current on this converter. So let's see if our video can work. Yes, here we go. So you can see at the moment I have near enough zero current. As I start to wind up the current, hopefully, here we go. As I start to wind up the current, this is closed loop. So the closed loop is increasing the duty cycle of the converter to maintain the output voltage under the higher load conditions. As we keep going about there, that's just on the borderline between discontinuous and continuous conduction mode. And if I continue to wind the current up after that, you can see the duty cycle doesn't actually change. We're operating in continuous conduction mode, but you can see the spike here. The energy contained in that leakage spike starts to increase because we've got higher peak currents on the primary side. So that's how flyback converters work. I mean, I haven't spent any time talking about control or magnetics design. That's going to be in later webinars. But from a topology perspective, essentially, that's really how they operate. Hopefully that was a useful introduction to what is a very commonly used topology, the flyback converter, and it operates with hard switching. Now, the reason I've jumped onto an LLC converter is this is a slightly different class of converter known as a resonant converter. So let's just take a straight away a look at the topology. And I've shown this is actually using a full bridge input and a full bridge rectifier on the output because of the power levels we've been working on here are a little bit higher than you could use a half bridge if you wanted to in different arrangements. But essentially this topology here represents a series resonant converter, or the LLC topology. Now, if I show our actual transformer model here, you can see here that we've got the same LM, we've got the ideal turns ratio. Now, the difference is on the LLC converter, I've called this inductance here LR, and it's in our equivalent circuit for our transformer, it's leakage, it's LL. The difference between an LLC converter and, for example, the flyback converter is in the flyback converter, remember that the leakage inductance was a problem for us. It creates loss and voltage stress, and it's a nasty thing. In an LLC converter, the wonderful thing about this topology is that this particular component forms part of the active circuit that forms part of the power transfer. So it's actually not something you're fighting against anymore. It's actually beneficial to the converter operation. In terms of explaining how an LLC converter works, I thought I'd do something a bit different here. I'd just show you some waveforms of a real converter on the bench, because I think it's quite useful to understand conceptually how they're operating before we get into the maths of how to model this sort of a converter. So we built this is roughly a 2 kilowatt capable LLC converter. And we built it using our rapid prototyping system called Hardware Stack. That's the black colored board system at the back. That system is forming the primary side circuit here. We've got 2 of the 3 active legs are switching. It's based on silicon carbides, but basically we're running that under constant frequency, which can be controlled by an external system via CAN bus. We've designed our own magnetics. So here in the middle is our it's a hand wound thing, so it's not particularly pretty. But we've got our main power transformer. We've got our resonant capacitor, the CR value here. And we've got an extra inductor here. So we didn't have quite enough inductance with our leakage inductance of that transformer. So we put some extra inductance in series with it to give it the correct value. This particular system uses this 32-bit Delfino for control, but it's running open loop. And in most of the examples, you'll see us running about 100 kilohertz, but we can change that frequency through CAN bus if we want to change the operating point of the converter. The magnetics we designed for 2 kilowatts, operating from a 600 volt DC link input. Now, for the more observant of you, you will have noticed that on the left-hand side of my screen, these parameter values just popped up out of thin air. There is a methodology you can go through to design these values. At the moment, I think it's more important to show you, if we were to use those values in a real converter, what waveforms does that give us? And then we can start talking about, well, why are these particular values what we've used? So this is our series resonant converter. And again, I'm going to show you a video in a moment of how this operates. The waveforms you can see on the scope here, the yellow trace at the top is the voltage on the center of the left-hand leg here. So it's going from 0 volts to about 600 volts here. If you can't read the scale, it's 500 volts per division, so 0 to 600 volts. The green trace is the voltage on the right-hand leg center point. Again, 0 to 600 volts, but the green and the yellow legs are run out of exactly out of phase at 50% duty cycle. So that sets up a square wave on the input to our transformer, or the resonant tank network, of plus and minus 600 volts at a 50% duty cycle at whatever switching frequency we're commanding these things to run at. The plot I'm showing you here, or the video in a moment, I'm going to vary the output power or the output current from this converter from 0 current to about 3.5 amps. And based on the frequency I'm running here, that gives us a maximum output voltage of about 430 volts at 3.5 amps, so about 1.5 kilowatts for the example plot I'm going to show you here. Before I press go on that video here, though, the waveforms you can see at the moment, and the orange trace at the bottom, is the current being drawn through the resonant tank network. Now, before I press go on this, I want to explain this particular waveform you can see at the moment is corresponding to a 0 output current on the output of our converter. And if you probably can't read the scale, it's actually for channel 3, this is at 5 amps per division. So it's going plus and minus 10 amps for 0 output power. Now that might seem like a crazy thing to do, but you'll see why it gives you a benefit in a moment. So under true 0 load conditions, our load is effectively infinity. This circuit doesn't pull any current really from the input. So from the perspective of the primary side circuit looking into the primary of the transformer, this is essentially open circuit. And what we end up getting from a primary side under 0 load conditions is this circuit here, which is CR, LR, and LM. So it forms a resonant tank network. Now, if I look at the impedance of CR, LR, and LM, you can see here that if I plot that impedance over frequency, if we're below the resonant frequency here, so the resonant frequency would be 1 upon 2 pi root LC. If we're below that frequency, well, the capacitor dominates behavior, and we get an impedance that looks like this, that comes down with frequency, and it behaves with a phase shift which looks like a capacitor. If we operate above that frequency, the opposite of that is true. We actually have a dominant behavior, or behavior dominated now by the complex impedance of the inductors. And from a perspective of the switching circuit looking in, it looks like an inductor. Now that's really important. So my operation, remember, is 100 kilohertz. So we're just operating into the inductive region here. So what do I mean by inductive region? Well, if you look at the green trace here, remember that's the voltage on the right-hand leg. If device M3 is on, which corresponds to the top here, so when device M3 is on, we've got 600 volts on the input to CR. And the current is about plus 10 amps in the notation I've drawn here. So we've got M3 is on and the current's flowing about 10 amps in the direction shown by the arrow. If I turn device M3 off, but don't turn the bottom device on, if I just turn device M3 off, the inductive current we've got flowing here will force the voltage on that leg to rapidly move down towards 0 volts. If I go back a few slides, it'll rapidly move down to 0 volts, and it'll actually try to drive below 0, but at a certain point, the body diode of the low side MOSFET M4 will turn on and clamp that to 0 volts. Now, if we let that happen and only switch on device M4 after the voltage here is slewed down to 0, we essentially turn device M4 on under 0 voltage conditions, and that means it's essentially 0 loss. So 0 voltage switching is a great thing here. Now, that only happens when you've got inductive current flow in the system here. If you had capacitive current flow, it would be a disaster. If you actually spend some time to work through all of the switching events here, you can see that if you operate in the inductive region with sufficient current in your resonant tank, then you can always guarantee that these devices will 0 voltage switch as long as you leave enough dead time for the voltage to slew down. And that has a massive impact on efficiency, which I'll show you in a slide in a minute. This slide here, it shows you actually just a zoom in of the switching voltage during one of those transitions. So, oh, actually, sorry, I've gone too far. I was going to show you a, where are we? I think maybe I just clicked, oh, it's gone. Bear with me a moment, folks. I should be able to show a video. Where's it gone? Okay, maybe I can't. Okay, I'll have to leave that. If I can get the video working at the end, I'll show you it. What the video showed you is that how those waveforms behave as you start to ramp up the output power. And actually, the plot at the top right here is a snapshot under the 1.5 kilowatt output load condition. So you can see we've started to get a slightly sinusoidal current sitting on top of this underlying current. But the most important thing is again, the current is still positive at the end of that switching cycle to force that 0 voltage switching. Now, if I zoom right in on that switching node, this is actually the falling edge of the yellow one, the rising edge of the green one. The time base here is such that the transition time from high to low here is around about 100 nanoseconds. And what's happening here is that the inductive load current we've got, as soon as we switch off the top side or the bottom side device, is of the right direction here. And in fact, it's in the plot I'm showing you here, the current's negative. And actually, so it's this one here. We turn this device off, the current's flowing back this way, and it forces the voltage here on the switching node, the green one, to rise. So what happens is that inductive load current is used to charge the total parasitic capacitance on that switching node from 0 to 600 volts or 600 volts to 0, depending on which edge you're on. Now, that parasitic capacitance is formed of primarily the body capacitance of these power devices here. It's formed by stray capacitance, which might just be PCB traces, or winding capacitance in your, in your resonant inductor here. The majority of it is probably your power devices. But the key thing here is we know how long it takes to do this, so that we know what DT is, we know the change in voltage, and we know the current that's driving that. So we can actually estimate the total capacitance on that node for that transition. And in our case here, we can calculate under that those operating conditions, we have an effective capacitance on that switching node of about 1.7 nanofarads of capacitance. Now, that doesn't sound like very much, but it is actually a fair amount. And the reason it's a reasonable amount is that the device we're using on our hardware stack is actually a fairly large silicon carbide power module that's capable of 50 amps, not just 10 amps. So it's we're actually operating a fairly large converter power module down at the bottom end of its range, which isn't really going to give us particularly great behavior, except for the fact here that we're 0 voltage switching, so we sort of get away with it. This system is actually capable of a few tens of kilowatts rather than just 2 kilowatts. So that's what's going on there. Now, that total capacitance of 1.72 nanofarads, what does that really mean? And it's quite a useful thing to do to compare. If we had a hard switch converter, and if we had a hard switch converter, then what happens is each time one of those MOSFETs on the primary side turns on, the energy contained in that that parasitic stray capacitance that you've got there, that total capacitance, is just dissipated. So if we just look at the energy, a half CV squared, well, at 600 volts, we'd have about 310 microjoules in that capacitance, that stray capacitance. However, each leg switches twice per fundamental switching cycle. So each fundamental switching cycle, 100 kilohertz here, we're losing about 620 microjoules. And remember, we've got 2 switching legs, so double that up again. So for this particular power stage, for one switching cycle, if we weren't 0 voltage switching, we'd actually be dissipating 1.24 millijoules per switching cycle. Now, to put that in context, if we were running at 100 kilohertz, if we didn't have ZVS operation, that would actually directly correlate into 124 watts of extra loss in our system. And for the measurement I've shown here, which was 1.5 kilowatts, that would be an efficiency which would be 8.3% poorer than the situation we actually have, because we can 0 voltage switch. We're not losing that energy. So 0 voltage switching and the LLC converter offer you very high efficiency because of this capability, but you have to make sure you design to operate in the inductive region. That particular converter, we did we put it through an automated test, which allowed us to operate under all these different operating points of it on the output. So we varied the output current from 0 up to about 8 amps. And we changed the switching frequency in an automated test from about, I think it was 100 kilohertz up to 250 kilohertz, something like that. And that allowed us to scope out the operating window of this converter and measure all sorts of things, including efficiency. So for this particular LLC converter, you can see that the 0 voltage switching capability we've got, even using this oversized module, has resulted in a system which gives us a peak efficiency of nearly 98%. Now that's incredibly high efficiency compared to a hard switch converter. And actually, we've built systems more efficient than this by actually concentrating then on loss mechanisms in the magnetics and actually choosing power devices which are more tailored towards the sort of operating point we want to have. You can also plot out the power loss contours here, which are essentially the same thing as the efficiency, but a slightly more useful way to represent power loss. This plots also give you an idea on one of the challenges of the LLC, in that you can't reduce the output voltage below a certain level really with these converters. And in this one here, we've done fairly well. We're going over an almost 2-to-1 ratio in output voltage and still maintaining good efficiency. The way an LLC converter works, though, as I'll explain in a few slides' time, is that we, rather than varying duty cycle, we vary that frequency of that square wave we're applying. And if you want to reduce the output voltage, you actually have to start increasing the frequency out to a fairly high level, at which point the behavior becomes a bit poorer. So you're rather restricted. So that's one of the downsides of the LLC. How do we go about modeling? So again, in the webinar this morning, I was trying to avoid using too much maths, but I think it's useful to understand the modeling approach used to predict LLC behavior. And it's something called the first harmonic approximation. Now, with that approach, what we're actually doing, because of the way the LLC converter works, you're operating fairly close to the resonant frequencies of that tank network. So what we end up doing is we represent the square waveform that we are actually delivering to that tank, and we just calculate what the fundamental component, what is the fundamental sine wave component, that it has the same energy level as the fundamental of that square wave. So how do we go about doing that? Well, if you remember back to university days, Fourier series is essentially what we can do. So this is the calculation of the Fourier series. We have 0 DC component, so AO is 0. I won't go through the whole calculation here because I'm sure you would not particularly appreciate that. All of this works through, you can work out what the harmonic content of that square wave is, and you get this expression, assuming that these are infinitely quick transitions rather than the actual slope, but that's a reasonable approximation. You can see that we have an expression whereby we have content at the fundamental, so at the same fundamental frequency as the square wave, and then we have contributions from odd order harmonics, so the third, fifth, seventh, and so on. And that's because this particular square wave is completely symmetrical. You just get odd order harmonics there. The important thing is the value of this fundamental here. So the first harmonic approximation, we're interested in the value of that particular fundamental component. Just to check that this does work, I thought I'd just reassemble that square wave from the first few harmonics. So that's just the fundamental, the 4V link upon pi sine omega t. If I add in the extra contribution from the third harmonic, we get this. If I add in the fifth harmonic, we get this. And if I add the seventh harmonic, we get this. So you can see the more harmonics we add, we're going back to that square wave. But from the purpose of our LLC design, we're just interested in that fundamental component. So stick with me on this. The first harmonic approximation gives us that harmonic level, which is 4V link upon pi. Step 2, the equivalent circuit here. So the next step is then to try and represent the output stage of this converter in terms of what the primary side circuit sees. Now, the voltage being developed, well, or at least when you're close to resonance, the voltage being developed across this primary winding is actually a square wave with a peak magnitude given by just the turns ratio times the output voltage. So you can perform a first harmonic approximation on that waveform again to give you the value of that sine wave there. And also, we know what the output current is looking like. It's a fairly much, if you're running at resonance, it's this sinusoidal looking waveform. If you then actually just divide those two together, the V pri FHA and I pri FHA, it gives you an effective impedance seen by the primary resonant tank, which is this RE term, So it gives you a way to represent an approximation of the output and take away all of that secondary side circuit and just represent this with an equivalent resistance. And that's quite a useful step to take, as we will see, hopefully, on the next slide. So if you can do that, what you end up doing with remember the first harmonic approximation of the input square wave. This is actually an image I took from a fantastic TI app note. If you want to look up some more detail on this, check out app note SLUP263. It's a fantastic treatment of the first harmonic approximation and modeling of this type of converter. And this really shows you that with this modeling approach, we're moving from a square wave representation of that circuit through to something whereby we have our output effective resistance RE fed by a sinusoidal circuit. This will become clear why we want to do this in a moment. If I just click down, the key thing here now is when you look at that linear sinusoidal circuit, you start to see that actually the way this works is that the LLC is effectively a high voltage potential divider. In a normal potential divider, you just have two resistors. Well, here we've got complex impedances rather than pure resistors, but the approach is the same. It's just the fact that those relative impedances change with frequency. So by changing frequency, we can change the gain of that potential high voltage potential divider network and therefore regulate the output voltage. As I mentioned on one of the first slides here, you have to operate above the lower resonant frequency formed by the CR and LM figures to make sure we always have inductive load flowing on the primary bridge to give us zero voltage switching. As we go up in frequency, the voltage you get delivered to RE, which essentially is the voltage delivered to the output referred back through to the primary, that reduces. So, and that's because the impedance of the LR component rises with frequency while RE stays constant. So we can, if we want to reduce the output voltage, we have to go up in frequency. For the die-hard math fans here, I've put in this equation. Again, this is a representation of that complex potential divider circuit here. The app note I mentioned goes into the far more detail on that. The key thing here is we form these equations here that give us a magnitude of gain of that network, which if you then work through the analysis of the system, we can give the output voltage is simply a turns ratio times the magnitude of that gain times the input voltage. So all of the terms except M are fixed. So M is the term that we're using frequency to vary the gain of the converter, so to respond to the regulation requirements of the system. These are some first harmonic approximation curves I've put together. Now, if you look at most of the literature, especially the application node I've described, people tend to plot out the magnitude M as a function of frequency. I thought I would actually, instead of doing that, plot out the output voltage for my converter I showed you, that LLC converter. I thought I'd put my turns ratio in there, the input voltage of 600 volts, and plot the value of M to give us our actual output voltage as a function of switching frequency. And I thought I'd do that for a number of different output load resistances which relate to the output power level of that converter. So the first thing to see here is that the FHA approach, it gives us an output voltage which is a function of frequency and load resistance. That's the first thing to note. Actually, I'll go back a step there. As we increase the load on the output, we start to reduce, or we start to operate on these lower curves. So as we go higher and higher in load, we can't necessarily get to the same output voltage. And as we reduce the load, we start to have a more peaking effect. The key thing here is that all of those curves pass through a single point. And that's the series resonant frequency, this FO figure, which is given by 1/2 pi root LRCR, and for my converter that's about 180 kilohertz. The interesting thing is that at the FO point, the gain of that M, the magnitude of M, is always unity, and that's quite an interesting point for how we operate this converter. I thought I'd also run some PSpice simulations just to see how close the first harmonic approximation is to at least to a simulation. So for the case whereby we've got 20 ohms on the output, so the purple trace, I ran simulations at 300, 200, 180, and 100 kilohertz. Now you can see here that when we're close to the series resonant frequency F0, the simulation and the first harmonic approximation compare very well. They're almost identical. As we go below resonance, the FHA model tends to underpredict the output voltage. And as we go above the self-resonant frequency, the FHA model gives us a higher voltage than we would get in practice. Now, this is one of those rare situations where actually that's quite helpful. I will plot out, so I did this the same for the 35.5 ohm, that's the yellow boxes here, the yellow circles, the 80 ohm case, and the 160 ohm case. And in all cases, that trend is the same. The FHA works really well near F0, but you get higher voltage than you expect below resonance and lower voltage above resonance. And that's quite neat for us, actually, because if you imagine you've got a system whereby the input voltage is moving around, or maybe you've got a battery charger where the output voltage needs to move by quite a lot. If the FHA were true, you'd have to go through a much wider range of operating frequencies to achieve those operating points. But in practice, you don't have to do that. The FHA model falls apart. So you actually you only need a narrower range of frequencies. You still need to design it correctly for your output load case, but you're always best running a simulation to make sure that you can meet those operating corner points. So the simulation shows excellent correlation to the first harmonic approximation at that FO point. We get divergence as we move away from that point. I mentioned the switching frequency of F0. You can see almost irrespective of the output load resistance, we have an output voltage which is constant. Now that essentially is saying that the LLC behavior is almost like a perfect voltage source. We can change the load around, but the voltage stays very stiff. And that gives you an idea that this particular converter for a particular operating point behaves almost like a voltage source converter. It moves away a little bit as you move away from resonance, but it's just one of the ways this particular converter works. In terms of a generalization here, as I said before, the magnitude of that gain curve is 1 when we're down at this point here. If I click through here, I'll go through the simulation points again. There we go. The magnitude M is 1 at this FO point. Now, if I want to increase my range of gain that I can achieve with my system, what can I actually do? Well, let's assume for the moment that the output load resistance and the turns ratio are fixed. What else can I actually do to increase that output range? Well, in the way that we've expressed QE in this modeling approach, to increase the gain range, we actually want to lower QE for a given load point. So if we want to be able to have our LLC tolerate a much bigger input voltage range, for example, we need to use a smaller resonant capacitor and a larger resonant, a smaller resonant inductor and a larger resonant capacitor. And that allows us to do that. However, what that does, if you think back to that very first slide I showed you on the LLC, where we've got that under no load condition, we've got that plus or minus 10 amps. As you make LR smaller and CR bigger, that no load current starts getting bigger and bigger because you end up with a whole load more energy moving around in that primary side resonant tank circuit. So to get a higher output voltage range, you need to be prepared to put more energy into your resonant tank network, which will make those components bigger, and potentially under certain load conditions, you might have to pay a bit in terms of efficiency. So we're just about coming to the end of these slides now, and I hinted at the start talking about bidirectional isolated DC to DC conversion. There's a really interesting topology known as the CLL or CL cubed C converter. What we do there is we take our standard LLC converter, which is the top left, and actually put rather than having standard diode rectifiers on the secondary side, we replace that with 4 active devices, a bit like our input inverter side bridge. And and then we put some extra capacitance and inductance. Now that turns this system into a natively controllable bidirectional power system. And it sort of makes sense really, because in any sort of a bidirectional system, you would sort of expect to look symmetrical, whether the power's going one way or the other. So in the CLLC converter here, there's a great deal of symmetry. I've drawn the magnetizing inductance on the what you might want to call the primary side here, but equally it could be referred over to the secondary side if you wanted to represent it like that. So this is a really symmetrical system, and when we're looking at the development of e-mobility and vehicle-to-grid type applications, the ability of your electric vehicle charger to either charge energy into the battery or in the same power stage send energy back into the grid, that's quite a neat feature. And especially when you can do it at the sort of efficiency levels, 98-ish% that is possible with this sort of a resonant topology. So if you've not played around with the LLC converter, I would strongly recommend taking a look at it, at least from a theoretical perspective. And if you get a chance to build one, even better, because you'll be amazed how well these systems can behave. They're slightly more complex to design than a traditional converter, but it's well worth the effort. I think just to summarize now, as I've said, there's many different types of isolated DC to DC converter topologies, all best suited for different sort of applications. And I've just chosen two today, which I think are two of the most useful. The flyback topology is really the most common low power topology you might find. It's a very effective way to perform low power isolated DC to DC conversion. So that's definitely worth learning. The LLC is an incredible topology. When you build one of these, especially at high power level, the waveforms look almost so perfect. It looks like a simulation, and you can't believe that it actually is a real signal on a scope. And they're great for high power because the efficiency is so good as well. The thing that's common between both those topologies, though, is that if you're able to natively operate any of those isolated topologies at higher frequency, it generally reduces the amount of energy storage you need in that isolation transformer, the high frequency transformer, which starts to reduce its size. In our later webinars, we're going to be talking in detail about high frequency magnetics design. You can only take this so far before other factors start to limit your ability to push switching frequency. But generally, if you can push switching frequency a little bit higher, it tends to reduce the size of your system and increase power density. And I think that brings us nicely to the end of this webinar. Thank you very much for attending today. I will just move over to see if we've got any questions in our inbox now. So bear with me a little bit. Okay. So yes, here's an interesting one. How can you design the leakage inductance of a transformer? It's an interesting question. It's quite a hard thing to design because it's a parasitic effect. If you're trying to design it from a perspective of a flyback to minimize it, what you need to start looking at is interleaved winding designs, whereby you can minimize that, but that has other challenges in terms of capacitance. However, if you're trying to utilize the leakage inductance in an LLC converter, you actually probably will find you need to do the opposite. You need to make the leakage bigger than you natively get. And we actually built, I think it was about a 700 or 800 watt LLC converter for a client a few years ago, whereby we were playing around with winding structures to try and get the right level of inductance, so we didn't have to use an external inductor. And ultimately you just need to separate the windings. Leakage inductance is flux generated by one coil which physically doesn't link to another coil. So physical separation can help with that, and we achieved that with that particular converter and got very good performance. You have to be careful of stray fields, though. There's no free lunch there, so it's always a bit of a balancing act. Let's have a quick look for some more questions here. So to design the LLC converter for megahertz frequency, LM becomes less, and to obtain this very low value of LM, the air gap required is I can't quite read that actually, bear with me a minute. I'm just going to widen this out. The air required is very high, which is not feasible. Is there any method to achieve the same? So LLC converters at megahertz, you've got to be a bit careful to try and get an LLC converter running at megahertz. It depends perhaps on the power level and the voltage level, but if you remember back to the LLC waveforms I showed you, we had that slew time between 0 to 600 volts took about 100 nanoseconds on that high power example. So if we were running at megahertz frequency, we'd only have 1 microsecond. Now 100 nanoseconds out of a 1 microsecond time frame is actually quite a lot. You might get away with that sort of frequency if you're operating maybe gallium nitride power devices and perhaps at lower power levels. Really, it's just then how you go about designing those magnetic components to give you the parameters you want. It's you just got to design for that particular frequency band. As you go up in frequency, it becomes probably harder to do that effectively. Also, the magnetics design becomes challenging because of the core loss, and the proximity type losses that you get in windings become a problem. So, unless it's a very low power LLC, I'm not sure. Well, it'd be interesting to build one and see how well it would work at megahertz. I think there could be some challenges there. So another question here, is the peak current also much greater for a converter in CCM versus DCM? Yes, that is true. For a given power level frequency, and topology, if you operate in CCM, the peak current in the primary switch will always be lower in CCM operation than it is in DCM operation, just because you in DCM operation you've just got much higher peaks. If you work through the maths, you'll see that comes out, or if you measure it on a scope, you'll see the same. Another question here, what is meant by cross-regulation? Oh, hang on, it's just moved. What is meant by cross-regulation for multiple output flyback converter? How does adding a dummy load provide better cross-regulation? That's a good question. So that flyback converter I showed you right back at the start of the presentation was actually a 2-output converter, plus or minus 15 volts. In that particular one, we actually just took regulation from the plus 15 volt rail to form our feedback. So the minus 15 volt rail pretty much just tried to follow what the plus 15 volt rail does. Now, you get the cross regulation is essentially how well one rail can maintain its voltage if the load on another rail changes significantly. And the worst case is when you've got an extreme load on one rail and effectively zero on the other. So what you do by putting a dummy load or a preload on a converter is you restrict the min to max ranges that particular converter can see in practice. And one other subtle thing also is that if you say, for example, you were running the 15 volt rail at full rated power with zero load on the minus 15 volts, well, what you'll get happening is that the minus 15 volt rail will peak charge. So its voltage will start to go closer to minus 20, minus 25, something like that. So by putting a preload on that on the minus 15 volt rail, you'll start to reduce the amount of peaking you get on that particular voltage rail. Also, if, for example, you were running zero load on your 15 volt regulated rail, it's going to be at 15 volts. If you put a heavy load on your minus 15 volt rail, it'll tend to sag. So you don't really ever want to go to zero load current under those conditions because it just causes one rail to move too much. We did some experiments years ago now looking at the sort of range of voltages that you can achieve through good cross regulation, typically for set-top boxes, that sort of stuff. If you can maintain a min to max voltage current change on a rail somewhere in the region of 30% to 100% load, we found that you could get about plus or minus 5% regulation. Depends on how you design the transformer and various other things, but that's about the limit. If you go lower than that, you might need to think about preloading or post-regulating, for example. I think we've got quite a lot of questions still coming in here. So a question just at the top here, how can we obtain the transfer function for the stability analysis for the LLC? That's an interesting one. It's quite complex. We're going to have a webinar later on in this series dedicated to control and modeling of switch mode power supply power stage frequency response. There's For standard fixed frequency stuff, it's reasonably straightforward using state space techniques to model the transfer function. For the LLC, it's far more complex. I don't think I've really got time to go through that today. The other thing you can do is look at it from an experimental perspective and actually do some system identification. Often people use that sort of an approach to model the system itself. Another question, how to ensure the LLC converter never enters the capacitive region. So with any of these LLC converters, you have to maintain a switching frequency above that critical frequency. Remember that the frequency governed by the resonance of the magnetizing inductance with the resonant capacitor value. If you can maintain your switching frequency above that, you'll be in the inductive region. In fact, most offline controller chips, that implement the LLC, they have to have a hard minimum frequency for exactly that reason, and you have to set that up. Otherwise, as soon as you enter the capacitive region, you can get all sorts of problems. You really need to keep away from that. So we'll take maybe one more question here. I apologize, we won't have time to do them all today. Actually, we've covered quite a few of these. So how can you overcome EMI issues at higher frequency? EMI is, we're going to have, again, a dedicated webinar talking about EMI later on in this series. It's a challenge. As you go up and up in frequency, dV by dt starts to increase, di by dt starts to increase. So those parasitic capacitances down to earth start to conduct more current, so you start to pick up more noise. You just have to be far more careful with how you design the system ultimately. And how you're looking at the whole system level EMI management. It's not straightforward as you go up in frequencies, especially when you look at gallium nitride devices are so fast, it's unbelievable. You can have dV by dTs in excess of 100 volts per nanosecond. And at those levels, the tiniest little bit of parasitic capacitance will cause you problems. So I think the best thing to do is prototype as early as you can in your development cycle, see where you are, and then move forward from that point. It's very hard to predict and mitigate these factors in advance. Okay, I think we'll probably stop there. Apologies if I've not had a chance to answer your questions today. Thank you very much for joining today. I appreciate it. It's possibly a bit late for some folk. I do hope it's been valuable. If you have been interested in the subjects we've talked about today, please do check out our website and look at the rest of the webinar series. We've got some of those already up on the website. And some of the ones next week, Jose will kindly be presenting, looking in some real detail of how silicon carbide devices operate and some of the things you need to think about. So once again, thank you very much for attending, and we'll hopefully see you next time. Bye-bye.